This is again machine interpretation of free text. Think about physician notes, nursing notes, text that you want to extract biomarkers about that can be fused with the other clinical measures into an analytics methods like the machine learning that we discussed, and we're going to get back to it a little bit later. But again, this is transforming unstructured free text into structured data elements. That's the name of this game here. All right, so read through the motivation, you know, I'm not going to go over it. So here, let's just look at one example. I've taken 5 of my classes. They all have syllabi. I've not taken the entire syllabus, just a little short description of it, just to show you the flavor, okay? HS 650, bootcamp, HS Health Sciences 853, 851, 850, 550. You know, here is a bit of the context of the syllabus, okay? Blah, blah, blah. It says something about, so I've got 5 documents. These are your 5 physician notes, okay? So the first thing that we want to do is we want to create a VCorpus object that includes all the text and some metadata about the text. So this is done by creating a column vector of the 5 documents, and we're going to call it docs, okay? And then the text mining package is one of the examples that you can do natural language processing in R. And when you pass these 5 docs as a vector of documents to the vector source and VCorpus, it does the VCorpus, and I'm printing here the VCorpus just to show you that it says, okay, you know, nothing really important, 5 documents in it. The VCorpus contains the 5 documents, so the first document is the first list, the first element in the list, and I can extract its content. And you can look in the documentation, this content could be a number of characters, for example. For each document, it can report various members of the object. So that's the first one. The first thing that you want to do with text mining is get rid of the crazy stuff, okay? Crazy stuff includes capital, lowercase, punctuations, apostrophes, endings and prefaces of words, verbalization of words, you know, the nonsense stuff. So that's what we're going to be doing first. In step number 1, we're going to be converting everything to lowercase because, well, I don't know, maybe sometimes capitals make a difference if there are abbreviations or something. So you got to be careful. Whatever the context is, you got to get rid of the nonsense because text carries a lot of nonsense, okay? So the first thing is to lowercase. This is how it's done. You use text mining mapping, and you provide a function you want to apply to lowercase. See how it converts everything to lowercase. There is no capital letters anymore. The next thing I'm going to do is I'm going to remove stop words. You know, I, me, us, them, you know, you, he, her, you know, that's irrelevant. Stop words, we're going to remove these things, and whatever, you can use different language. This doesn't have to be done in English. Whatever the text is, there is stop words in different languages. You can see which languages, obviously, there is at least 200 languages. I guarantee you not all of them have the stop words defined, but you can define your own stop words. You can define, I just want to remove these stop words, period, and that's what you can do. And here is where I say stop words. Again, this could be, you're not happy with this, well, define your own stop words, remove them. Now the text begins to be terser, very terse, human readable, not, but machine interpretable, yes. So, okay, so you see how we go, we simplify a little bit. And next what we're going to do is, yeah, so here is your own words, remove them. You're going to remove extra white spaces, tabs, you know, stuff that's not information carrying. Okay, strip white spaces we're going to do next. And this is oftentimes, you know, there's multiple white spaces, tabs, look as spaces sometimes. You know, you've seen sometimes a tab, which is typically 6 characters long, can actually look at a single character, depending upon how is it positioned in the order of the text. Removing punctuations, you know, here's the command. So now look, now this is just, you know, I'm switching back and forth between first document, second document, just to show you how the elements in the list of documents can be indexed. So you see stuff got removed here, you know, everything is in the lowercase, there is no dots, there is no exclamation points, etc. So we're going to convert back to original text by saying plain text document. And then we're going to be stemming or removing of plurals and action suffixes. In the English language, at least, there is a lot of these things. So for example, well, we need to look at these, write the S's and whatnot get removed. So here's the second one. And then once we remove all these action words, look what happens with the text. Science became science. Predictive became predict. Analytics became analytic. It essentially finds the roots of words. Because remember, analytical, analytics. Well, what's the difference? It's the same thing when you start counting. So it becomes less human-pleasingly readable, but very consistent. And now we can begin to tabulate how frequently are various kernels of words appearing. So bags of words refers to these engrams that kind of tell you how many. What's a phrase? A 2 gram is a word of 2 phrases, a phrase of 2 words, etc. And then you construct what's called a document term matrix, okay, from the corpus once you go through all the pre-processing steps. And the document term matrix has some additional things, right? It has, you have your 5 documents have 329 terms, 5 documents. Non-sparse are 540 words are non-sparse or frequently occurring words, and 1100 are sparse words. The sparsity rate is 67%. And here's a little bit of a description of these. And then you can inspect the document term matrix. So here is, for instance, the frequencies of analytic appearing in the 5 documents. It doesn't appear very frequently in the 4th document. And look at data. Data appears predominantly in the 1st document. Inference appears predominantly in the 4th document. So at this point you can begin to look at some of these documents begin to look different based upon some of these frequency counts. And now here you do find the frequency terms but exclude the low frequency counts. Anything below 2 is going to be excluded. So it only prints the frequently occurring terms. Okay. You can also print the terms that are highly correlative. So what highly correlates with statistics? Well, epidemiology, 95% correlated. Publishing, studies, theoretical understanding. So they kind of, this is the correlation limit. You set up the correlation limit and it reports for you which words correlate with these. So let's go ahead and do a case study, very quickly. So I'm going to be looking, because this first example is kind of mock-up. Who wants to look at my syllabi? So let's look at something that does make sense though. We have US job rankings data. the top 200 jobs in the United States, and they're probably across the globe the same, they're rank ordered according to various criteria, okay? For example, stress level, payment, opportunities for jobs, compensation levels, you know, variety of things. And there is an overall ranking of these jobs. You can look them up. It's a very interesting study. You know, the more hands-on the jobs are, lifting, carrying stuff, you know, they kind of tend to the bottom because they have high physical stress, you know, the compensation levels are, you know, the manual jobs tend to be on the bottom, the more cerebral jobs, if I may call them this way, tend to be more on the top, and whatnot. So, but they have something very important these days. We have job descriptions, you guys. So get this now. We have a bunch of quantitative measures for this data set, and we have the clinical notes, which in our case are job descriptions. Now, what I want to do is I want to pull the job descriptions, I want to synthesize that information, and then I want to try to do prediction of the ranking of the job based upon a job description. You know, wouldn't that be cool? Because once you have that model, think about it. You have a model that's purely based on data, including the free text of the job description, to predict the job rank. You can design an algorithm that goes online to my job search site, pulls out all the job description, ranks them for me and says, go ahead and apply for these 5 jobs. You probably do well. You know, it's very interesting, right? And you can do this thing obviously with patients. So very quickly through, you guys can look at this. Here is some of the stuff. You know, by the way, the job description, this is interesting here. They have these underscores in the job descriptions replacing spaces because we wanted to use this as a single string. If somebody loads this in some kind of a software that separates things based on space, we don't want to be incorrectly interpreted. So we've put underscores to replace all spaces, okay? So we're going to get rid of these underscores later, okay? They're just placeholders to make this job description a single contiguous string. Is everybody here with me? So don't worry about that. So you go through the process, this, that, and the other. Oops. Okay, so you go through the process, and I'm just printing the top, the top 10. So remember, there is 200 jobs. So these are my cases, and we have hundreds of different terms. Okay. And you can see, okay, so document 1, will, abnormal, access, you know, whatever, activity and whatnot. And again, you can sort the top, calculate the cumulative frequencies of words across the documents and sort them out. So develop, assist, you know, these are the corresponding frequencies. And the corresponding frequencies for the bottom 100 jobs. So I'm kind of artificially here splitting the top 30 jobs and the bottom 100 jobs. And there's some in between that I'm just ignoring for now. Yeah. Why? Well, you can choose whatever you want to do. Look at the difference between the frequencies of terms. The top jobs, the more cerebral, creative jobs, develop, assist, natural, study, analyze, concern, inform, treat, theory, scientific, research problem, etc. Look at the bottom 100 jobs. Operate, repair, perform, install, build, prepare, manufacture, machining, you know, stuff like that. The hands-on stuff. You know, you gotta be strong for these jobs. And I mean physically strong and mentally strong, you know, to put up with something like this. Okay, and we can do some plots here for the highly frequent jobs, you know. So again, these are the bottom 100 jobs printed, the corresponding plot for the frequencies of the top 30 jobs. And then you can look at intersect. Are there an intersection? Well, 2 words are intersecting in both of these job descriptions. and they're industry and business, apparently. You can construct word clouds of these for each cohort if you want. And now what we want to do is we want to dichotomize, construct a new variable called job high rank, which basically says if the index of the job, because they're rank order, when the top jobs are listed on the top, they're not randomly listed, is what I'm saying. So I can use this very simple separator, top 30 job, yes or no. And now we're going to get the GOM net, okay, and we're going to try to predict the top 30 job or not. Okay. So here is your lasso penalty. Oh, and by the way, okay, so the prediction, you guys, is going to be the document term matrix, and the outcome is going to be my own defined job rank, which simply is a binary thing. Binary thing, top 30 or not. You can choose anything you want, right? By changing this model. Right now, I'm gonna stick with legit model, and I'm gonna use cross validation, okay? And I'm gonna use I'm gonna penalize using lasso, and my measure is not gonna be the root mean square as we did before. It's gonna be the area under the curve. We're gonna use tenfolds cross validation, and threshold of 10 to the minus third, lower number of iterations, etc., etc. And now here is the plot that we've seen before. The area under the curve, remember, the area under the curve, if it's above 0.5, is good, is reasonable. As it approaches 1, is getting really better. So you're at about 70% with, look at this, 4 features, you're at about 75% or so predictive power. This vertical line tells me that I probably have, no, it's 4 or 5 features, I'm not sure exactly. And this is the penalty term. Log of lambda is minus 2.5. Exponentiate this to find lambda. Okay, and here is how you extract from the fit model. You extract the maximum area under the curve, ends up being 72-73%. That's not a bad classifier for completely being out of the box. Then we're going to define 2 things, the term frequency and inverse document frequency. So these are various ratios that tell you how common or uncommon various things are. And you can do the same thing with this TF IDF matrix. And in this case, your area under the curve is slightly lowered, but roughly speaking on the same side. Now let's go ahead and do a prediction using fit1, which was this latest model that we fit. So see, if you predict on the actual training data that you used, wait, let me just see here. Oh, okay, because the predicted values that you get are probability values, you guys. Think about that. The predicted values are probability values. They're not binary 0, 1, or yes, top 30, or no, bottom 170. So what I'm doing here is I'm saying if the predicted probability is below 0.5, let's just call this a non-top 30 job. And if the predicted probability exceeds 0.5, I'm going to call it a top 30 job. And then we're going to compare these binarized predictions against the very same training data. There is no testing data here. But we almost get, we get it perfect, right? 29 jobs but there were supposed to be 30 here. Oh, because I had strict inequality, you guys. Actually, I'm looking at top 29. Remember? That's why I'm getting 29. I was expecting to see 30 here and 170. The reason why it's 29 is that my criterion, when I define these variable, I said top 30 but less than. So I'm having a strict inequality. That's why I'm getting 29. But it's perfect prediction, apparently. And then right. And now comes the interesting part. Remember, because we trained on the entire data set, but I want to test how does this model work on prospective text, prospective job descriptions. And I'll get this is the real situation now. A new clinical note arrives. You need to classify is the subject patient or a control, presence or absence of a disorder. So what I went ahead and I looked at the Bureau of Labor Statistics in the US has thousands and thousands of job categories. For each of them, they have job descriptions. So I figured, let's look at some of these. They have nothing to do with the job descriptions that I just showed. They're completely independent. This is the feds, the federal government definitions. They're crazy different definitions. They're very, you've seen government definitions of jobs and you've seen the industry definitions of jobs, right? They're very, very different. So these guys are very rigid. So here are 3 jobs. They may be jobs describing professions that are not included in the 200 that I showed you. They're just random jobs. So the first one is, I'm going to call it accountant. So this is going to be my prediction. The prediction text for the first job is going to be called test accountant. And here is the job description that comes directly from the Bureau of Labor Statistics. The second job is a job for an attorney, and it says, performs blah, 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 categories, whatever, long job description. And the last one is the job description for a machinist, operator of heavy equipment, and that's what it says. That's the work stuff that they do. So let's go ahead and put these JDs, job descriptions, into a column vector, right? So I've got 3 columns, text. Let's process them, pre-process them, and all that business. Okay. Remove the spaces, pre-process this and that. Create vocabulary from these jobs. Remove stop words, whatever. Progress. Vectorize this vocabulary, and then construct the term document matrix for these test JDs. Okay. And then the dimension. Okay. The training data set is the data set that we trained on, and it had 200 jobs and 2,675 terms. Okay. The dimension of the testing jobs, I've got only 3 job descriptions. I can put in as many as I want. And they also they use the same vocabulary. You have to, because if you learn on English and try it on Chinese or something, it ain't gonna work too well. So you gotta use the same vocabulary to train on. So here is now where we're gonna test on. Okay, no, we are fitting the model on the training jobs. Okay, and then we are going to predict on the testing jobs. We're going to predict where, if these 3 professions, I don't know if these professions are listed in 200 jobs, but if they were, what is going to be their ranking? Are they going to be top 30 or not? That's the question, right? Is everybody here with me? All right, so it tells me that the probability values associated with these 3 jobs to be a top 30 are 21, 22%, 22%, and 12%. Okay? And now you look at this thing and say, well, inconclusive. Now remember, the first job was an accountant, the second job was an attorney, and the third job, I intentionally picked them up to be very different. The third job was the machinist. Okay? Now notice that the machinist has a much lower probability value, but so did the other ones, 22%, you know, I mean that's not very top 30. Until you guys look at the probabilities for applying the same model on the actual 200 jobs that we learned on. And you see these probabilities are, for the top job was 30%, 40, and then 12. The third job had a very low rank, but most of the other ones are kind of in the 20s, 30s, a few 12. But as you go down towards the bottom, look what happens. They're all 12%. So the bottom jobs have very low likelihoods. Is everybody here with me? So the point I'm trying to get across is that if you try to introduce a dichotomous test of whether one of these jobs is going to be a top 30 or bottom 170, you don't threshold at 0.5. You need to threshold at a lower probability value. And I don't know what this probability value is, but looking at these data, it tells me it's probably going to be 15%. All the way up to here, look. 13%, okay. And now at this point, at some point, they begin to increase. 14, 22, you know, whatever. So if you set up a threshold of something like 20% or so, most of the top jobs, most, not all, but most of the top jobs exceed 0.2, right? So if you set your threshold at 0.2, the accountant and the attorney, they are going to be considered top 30 job, and the machinist is way down, right? Okay? So this, I hope, kind of conveys to you the idea of how these things can be done. Context from the textual unstructured input can be contextualized to feed in as these term design matrices into the model to do some prediction. Okay, that's that. And then there is a very nice example, if anybody's interested, sentiment analysis. The same thing, except that in this case it's for movie critiques. Whether or not the verbose description of the critique says that the movie was highly ranked or lowly ranked. So anyways, look at these things. The data is here. So that's one. So let's, again, here's the source code. You can look at that.